Hello, for some reason that I don't know, the last 20 minutes of the last lecture was not recorded, so I will redo it here. And because here I have enough time, so I will not go as fast as I usually do during the lessons. So the last thing I was talking there was about the method of U substitution as a technique of integration, which is, I would say, the most important technique that you need to be good in calculating integrals using this method. Okay, so and then the starting point was actually the chain rule. So you know that f of g of x, f after g, if I want to differentiate it, the answer will be f prime of gx times g prime of x, yes? This is the chain rule. So if I integrate both sides now, then it means that the integral of the right hand side, f prime of g of x, times g prime of x dx becomes equal to the integral of f after gx prime dx. Well, we know that the integration is somehow the inverse of differentiation. So I have derivative. I am differentiating this function first and then I integrate. So this integration will undoes whatever differentiation does, but of course up to a constant. So it becomes f of g of x and then plus c. And usually it is easier to denote g by u, so that's the reason we call it a u substitution. So in that case, what happens, instead of this g, I put u, and then this becomes u prime. So the left hand side will be integral, so let me change my color, integral of f of u, g prime becomes u prime dx, I have a prime here as well, and then on the right hand side I will have f of u plus c. And it is common that this combination is called the differential of u, and it is denoted by du. So if you want to write the chain rule version of integration, it will be f prime of u du is equal to f of u plus c. So exactly as if we are working with x. Do you remember integral of f prime x dx was equal to f of x plus c? So this means that the method of substitution allows us to use the same idea, but by introducing a new variable u. Okay? So now, for example, let us solve some other problems from the lecture notes. Okay, so let us do number 2 here. Okay, so let us solve this problem. As I told you during the lesson, I told you usually if you want to see which part of the integrand is good to take u, the main idea is that if you take that u, its derivative up to multiplicative constant appears in the integrand somewhere as a factor. Of course, if that is the motivation, I mean, if this is your strategy, it is not hard to see that it would be a good idea if we introduce u to be x minus 3. But as soon as you realize that this is what you're supposed to do, the rest of it is something like an algorithm. You differentiate both sides. You take differentials from both sides. Differential of u on the left means take the derivative of u with respect to u, which is just 1, and multiply it by the differential of u, which we denoted like this. And if I want to take the differential from the right hand side, I differentiate my function with respect to its variable, which becomes 1, then I multiply it by dx. So this becomes just simply dx. And then the point is that rewrite your original integral in a way that you cannot see any track of the old variable. Everything should be switched to the new variable. Okay, so this means that when I go here, instead of x minus 3, I don't have any problems. I can just replace it with u. Instead of dx, I don't have any problems. I just replace it with u. But then you see that there is an x left there. You are not supposed to leave it. Like everything should be switched to the new variable u. Okay, because of that, this will motivate you go backward and try to calculate x in terms of u. So I move 3 to the other side, x becomes u plus 3. Now everything is ready. So my integral, so let me call my integral I here. The integral I becomes equal to the integral, instead of this x that you see here, I put u plus 3. And then I have square root of x minus 3. But x minus 3 is nothing except u, so this becomes simply square root of u. And then dx is just du, so this becomes du. But this is doable. Why? Because I can expand it. So I can write it as u square root of u. I'm multiplying it in. So 3 square root of u and the whole expression du. Okay, so now I can split it, but I can write it as u times u to power 1/2. So it becomes u to the power of 3 over 2. And this can also be written as 3u to power 1 over 2. So if I open up the integral and make two integrals out of it, it becomes integral of the first one, u to the 3/2 du, and then plus 3 is a multiplicative constant, so I pull it out, then integral of u to power 1/2 du. And in both cases, I will use this formula. So if I have integral of u to power r du, we learned that if r is not equal to -1, then what I can do, I can write it as u to power r plus 1 divided by r plus 1, and then plus a constant. So here, I will use this formula. I give the role of r to 3/2. And here I use the same formula, but I give the role of r to 1/2. So then it becomes, so let me change my color. So this becomes 1 over 3/2 plus 1. And then u to the power of 3/2 plus 1. And then here I have a 3. And then I will have 1 over 1/2 plus 1. And then u to the power of 1/2 plus 1, and then I add the constant of integration at the end. Okay, but if you calculate this, this is 5 over 2, but because 1 over 5 over 2 becomes 2/5, and then u to the power of 5 over 2, and then plus, if you do this calculation, it is 3 over 2, this 3 and that 3 cancels, and 2 goes up, so this becomes 2 u to the power of 3/2, and then you have a c. But you shouldn't forget you have to replace u with original variable x. So u is x minus 3, so wherever I see u, I put x minus 3. So this becomes 2/5 of x minus 3 to the power of 5 over 2 plus 2 times x minus 3 to the power of 3 over 2, and then plus a constant. So that will be the answer to this integral. Okay, now let us solve this problem from the lecture notes. Okay, so this is the integral that we want to calculate, so let me call it I. And of course you can see that immediately you can write it in this form, and you will see why this is useful. I write it as e to the arctangent of x, and then multiplied by 1 over 1 plus x squared dx. Now it becomes clear that this is a good candidate for taking it u. Why? Because you know that the derivative of arctangent is 1 over 1 plus x squared. So as I told you, whenever you see that there is an expression in the integrand whose derivative appears as a multiplicative factor to the integrand itself, it's already good indication that this is good to take u. Okay, so now that everything becomes clear, so I would write it as u, arctangent of x, but the rest is algorithmic actually. So what you do, you find differentials, the left hand side du, the right hand side, the derivative of arctangent is 1 over 1 plus x squared dx. And now immediately it becomes clear that this part is your du here. You see that I calculated this one, became du, and this is nothing except e to power u. Yes, so this means that this integral can be written as integral e to power u du. But we just learned today how we can calculate this. I want a function whose derivative with respect to u becomes e to power u. It's very simple. It's e to power u itself and then plus a constant. But you shouldn't leave it like this because we have to switch back to the original variable. U is arctangent of x, so it becomes e to power arctangent of x, and then I have a constant c. Okay, so now let us go and solve this problem. Okay, so that is also easy. You see that immediately. If I take this one to be u, what is the derivative of this expression? It becomes minus sine x. And of course you see that a sine x appears there, and this minus sign is just minus 1, which, as I told you, it's an up to scaling factor. That's not a problem because we can always fix that. So here it motivates me to take this expression to be u. So I will take u to be 1 plus 2 cosine x, but then immediately the rest of it becomes an algorithm. So I calculate the left-hand side, the derivatives. So the left-hand side becomes du, the right-hand side, the derivative of 2 cosine x becomes minus 2 sine x, but I multiply it by dx. But now what you need is this combination, because I want to write everything in terms of new variable u. In the denominator I don't have any problems because I just simply replace it with u. But this is sine x, this is dx. I don't like to have them. I want to have everything in terms of u. So this means that this expression is exactly the one that appears here. So this motivates me to divide everything by minus 2. So it becomes minus a half du. The right hand side becomes exactly the combination I would need for this problem. So now if I call my integral I, so the integral I becomes equal to integral. Instead of this expression, you see, I can put minus a half du, so I can write minus a half du. And in the denominator, I can write the square root of, but what 1 plus 2 cosine x is nothing except u. But minus a half is a multiplicative constant. I pull it out. Then I will have integral 1 over a square root of u du. So this is one of those integrals that I have in my memory. If you don't have it, you have to calculate it every time. So it becomes minus a half. Then I would write this as u to power 1/2 and bring it up. So it becomes u to power minus a half du. But then I would write minus a half, and this is now a famous formula. So integral of u to power r du becomes u to power r plus 1 divided by r plus 1, yes? So this becomes 1 over r plus 1 minus a half plus 1, u to power minus a half plus 1. So if I simplify everything, so this number becomes 1 over 2, it goes up and they will be simplified. There will be a minus sign left. So it will be minus u to power minus u to power 1/2. Yes, so it will be plus c. Oh, I forgot to write a plus c here, a plus c there. So it becomes minus the square root of u plus c. And then instead of u, I write 1 plus 2x. So it becomes minus the square root of 1 plus 2 cosine x. And then I have plus c. So what does it mean? It means that this is the set of all functions whose derivative is this function. Yes? Okay, so now this is also a good question. Let us solve this one as well. Okay, this one might be a little bit more tricky because at the first glance it seems that there is nothing that I can take u because the derivative of none of these parts become a factor, is a multiplicative factor in the integrand itself. For example, if I take this to be u, which is something comes to mind usually, so then what happens, this becomes 3 plus 2x squared. When I differentiate, the right hand side becomes 4x dx. So I do not have x dx. 4 and 12 are not big problems, I can fix them, but x to power 3 is not something that I want. but still it will work. Let me tell you how. So I will still take u, so let me call this integral I again. So I will take u to be the same expression I guessed in the beginning, and I do the standard method, so du becomes the derivative of the right hand side, which is 4x dx. Okay, but now the problem is that my strategy is to eliminate x everywhere in favor of u. I don't have any problems here, but still I have a little bit of problem here because that is x to power 3. So it motivates, but what I have here is x dx, not x3 dx. Okay, so it might motivate us to do this. Instead of 12x cubed, I can write it as 3x cubed multiplied by 4x, not 3x cubed, 3x squared multiplied by 4x, and then I copy and paste the denominator, and then dx. Okay? First of all, this is valid, because if I multiply these two, I will get this back. So I haven't done something wrong, so this is legal. But the point is that when I do that, this part now becomes du, and this part becomes the square root of u, so I am getting closer to my goal to eliminate x, but still this x squared is left. But that is also not an obstacle. You know why? Because now I can switch here and calculate x squared. So I move 3 to the left, becomes 2x squared, and I divide everything by 2, so it becomes 1/2 u minus 3 is equal to x squared. Now everything is ready. So here, instead of x squared, I can write this expression in terms of u. Instead of 4x dx, I can write du. And instead of this expression, I can write square root of u. So I am done, more or less. Okay, so this becomes integral 3 times, instead of x squared, I put 1/2 u minus 3. And then instead of 4x dx, I can simply put du. So let me write du in front of the fraction line. And then divided by square root of u. But that is easy now to calculate. 3/2, I can pull it out. And then I will have u minus 3. And instead of square root of u, I write u to power 1/2 du. And from the experience we got in the very first examples of lesson, so I can write it as u divided by u to power 1/2 minus 3 divided by u to power 1/2. And then totally du. Okay, so this becomes 3/2. Integral u divided by u to power 1/2 becomes u to power 1/2. And the other u to power 1/2, I bring it up, so it becomes minus 3u to power minus 1/2 du. But now I can break it into two integrals. Remember, there is a factor of 3/2 outside, so I open a pair of brackets, and then I open up my integral. So it becomes integral of the first one, and then minus 3 is a multiplicative constant. I pull it out, u to power minus 1/2 du. And now in both of these integrals, I can do it easily. So it becomes 3/2. The first integral becomes u to power 1 more, which is 3/2, divided by 3/2. But when I divide by 3/2, it is equivalent to multiply by 2/3. And then, okay, so let me open this pair of brackets and do it in 2 steps. So what I am doing here, this 3/2 is this 3/2, and the answer to this is 2/3 of u to power 3/2. Then I will have a minus 3 here, and then u to power 1 unit more divided by 1 unit more. So it becomes 1/2. So it becomes 2u to power 1/2. And then finally I close it, and then plus sc. So if you don't mind, let me now multiply this factor in. So these are cancelled. So it is just u to the power of 3/2. And then I multiply this here. This 2 and that 2 are cancelled. 3 times 3 is 9. So it is minus 9 u to power 1/2 plus c. I prefer to write it in terms of square roots, so it becomes u square root of u minus 9 square root of u plus c. And then I replace u with this expression, so the answer will be 3 plus 2x squared multiplied by square root of 3 plus 2x squared minus 9 square root of 3 plus 2x squared and then plus c. Okay, so let us finally solve this one. Okay, so in order to do this, so might be, I don't know, for example, if you are not very experienced, you might be motivated to take this one to be u, but if you take that one to be u, then du becomes 1 over 2 square root of x dx. So it is not that bad, because you have this dx, you have this in the denominator as you want, and this factor is not a big problem. We can always multiply or divide by constants without affecting that much the problem. But it is not useful here, because this one I am in trouble. Of course, I can write it as integral 2 sine u, if I do that, cosine u, and instead of dx over square root of x, I can put 2 du. I mean, it's not wrong, but you don't need to do it like this, because then if you arrive to this one, you have to do another substitution. For example, I don't know, we can call it t substitution, by taking sine u to be t, and then calculate again. And then you have to go back 2 times, from t to u, and then from u back to the original variable x. But if you, if you're a little bit experienced, you might also consider this for u, just the whole expression sine square root of x. Why this is useful? Because if I continue as normal, so I will have du on the right hand side, I have to differentiate it and then put a dx. To differentiate this, I have to use the chain rule. Sine of a function of x, the derivative of sine of a function becomes cosine of that function, multiplied by the derivative of that function, which is 1 over 2 square root of x, and then finally you put dx. So that is good, because if I combine it, it becomes 1 over 2 cosine square root of x divided by square root of x, then multiplied by d of x. So that's very good, because you see this expression is exactly this one. So the only thing that I have to take care is this 1/2, and that's not a big problem. I just multiply this and that by a factor of 2. So then it becomes 2u, and this will be cancelled, and that's exactly what I need. So this means that 2 du becomes equal to cosine square root of x divided by square root of x dx. Okay, so if I call my integral I can immediately write it in terms of my new variable u. So what I do, instead of this expression, I put u, so it becomes 2 to power u. And then instead of this expression, which is exactly this one, I put 2 du. So this becomes times 2 du. But this 2 is just a multiplicative constant, so I pull it out, so it becomes 2 integral of 2 to the power of u du. And in the beginning of this lesson today, we learned that integral of a to power kx dx is 1 over k ln of a to power kx plus a constant. So if you compare this one with this one, first of all, a in this problem is 2, and k, as of course x variable is now u variable, it doesn't matter, so you can write it in terms of u if you want to. But the point is that this k, which is the coefficient of u or x, is 1 in this problem. So what I do, I would write it as 2, which is that constant, but instead of integral of 2 to power u, I would write 1 over k is 1, ln of a is 2, so it's ln of 2, and then the function itself, 2 to power u, and then plus my constant. So then I can write it as So I can, for example, multiply this 2 by this 2 to power u plus 1. So this becomes, so I multiply them, it becomes 2u plus 1, and then divided by ln of 2, and then plus a constant c. But I have to switch back to my original variable. Instead of u, I can put this expression. So it becomes 2 to the power of 1 plus sine square root of x, and then divided by ln of 2, and then I have this constant c. And that's the answer to this problem as well. Okay, during today's lesson, I also started talking about integration by parts. I will actually make another video for that small part. And then, of course, we can continue with tomorrow during the lesson. Thank you very much.